basically up to now we know a lot of things. So let's just recap everything that we have done so far. We know some idea of random sampling. We know that it helps us collecting the data for the estimation of unknown population parameters. We know two things from the asymptotic theory, weak law of large numbers, and central limit theorem. We know that if we collect large enough sample, but it must not be close to the population size, we also know this, then the estimator x bar converges in probability to mu. So the probability that our result will deviate from the target parameter shrinks to 0. And the distribution of this estimator converges to the normal distribution. So this last thing helps us to apply all those questions about confidence intervals, about hypothesis testing, if we don't know the underlying probability distribution, but we have large enough sample, because with the help of central limit theorem, we can ensure that approximately our result in the large sample is gonna be normally distributed, and then it gives us a chance to estimate the confidence interval, to apply the hypothesis tests, and so on. So this is a very important thing that you need to understand. So you cannot always use those tests and those confidence intervals and all those things. Only you can use them if your sample is large enough to apply the central limit theorem. That's an important thing to understand. Well, we know how to establish the estimators with the help of method of moments and method of maximum likelihood. If we are not interested in the sample average only, but if you want to estimate something else, and you had the exercise sessions and home assignments when you needed to estimate some other parameters, but you see that those parameters sometimes are linked to the sample average. So that's why we are mostly discussing the procedures concerning the sample average. So we know that with the help of point estimators and confidence intervals, we can infer the location of the unknown population parameter within some boundaries with the given probability. And lastly, we established the toolbox of hypothesis testing, and it helps us to answer some questions whether the population parameter belongs to the particular interval or not. So we state a null hypothesis, we state an alternative hypothesis, we collect an evidence in the form of a sample, and then if the evidence contradicts the null hypothesis, because the distribution of a sampling statistic states that this is highly unlikely, then we reject the null hypothesis, for example, or we cannot reject it because the sample does not contradict this. So all of this we had. You are gonna have the exercise session on hypothesis testing, so I hope you will also master some calculations. That's why I want you to watch the video once again to see how this works. Well, but in practice, so at this moment, we have established almost everything that we need to apply in practice our statistical tools. So we have discussed with you in the last lecture of econometrics what are the practical questions that we can pose about the causal relationship between treatment and the result, and about the causal relationship between different variables. So basically, in practice, we want to make conclusions about the joint distributions of random variables. So not only one, and we are not interested in the particular parameter of a variable. Well, there are some applications I demonstrated you about the about the random walk hypothesis, for example, well, it's possible to apply for only one variable. But there are much more situations when we are interested in the joint distribution of random variables and their mutual dependency, causal effects, etc. So today we will discuss how to compare two samples and how to make inferences about parameters of two samples. And well, this is the first step into understanding of these causal effects and how we can estimate them. Okay, so we will start with the idea, what we are gonna do. This slide will be similar to our discussion of the randomized control experiment in econometrics. So we can make an experiment, and in the experiment we will get the result in the form of two samples, and those two samples can be regarded as independent of each other. So if you remember Friday's lecture in econometrics, we spoke how, for example, we want to understand what is the effect of, what was the example? We wanted to understand what is the effect of, who can remind me, what was the example in econometrics? Of a master degree on the future salary, right? Well, and we said that we want to collect a sample. Well, first of all, we want to run an experiment, randomly assign some people to go and obtain this master degree, some people do not obtain this master degree. Well, basically, we randomly assign those people who go and receive this master degree and who doesn't. And those two samples are going to be independent of each other, right? So we want to understand. So for example, there is one example in medical study. A sample of subjects may be assigned to a particular treatment, and another independent sample may be assigned to a control or placebo treatment. So you probably have heard how the testing of vaccines against COVID has been done. That's exactly what we see here. Or that example about the master degree and random assignment of this master degree. Well, in principle, we have two samples. One is a treatment sample, another is a control sample, and yes, we randomly assign people into these treatment and placebo groups, and then we want to some numeric outcome of this experiment. Also, in the business practice, you can hear about what is called A/B tests. If you try to search for the working positions in the data analysis field, you will immediately see this acronym A/B test. Why? Because this A/B test is the same as a control experiment. It's the same as in medicine, but it is applied in some business practice. For example, I took this from Wikipedia article on exactly on A/B tests. So look, we have two different designs for the internet site here and here. One button is the blue one and the other button is the green one. And we are not sure which button will attract more consumers, which button will be, for example, will have the higher click rate. What we can do? We can randomly assign some users who visit our site, who visit our page to see this blue button, and some users randomly will see the green button with this small arrow, which probably motivates people to click there. And then we collect the data on the click rate, right? So we can see, well, this button has been clicked in 52% by 52% of visitors, and this button has been clicked by 72% of visitors. Is this enough evidence to claim that this design is better and attracts more clicks than this? Well, and here is the question of statistics, because we know that this is a random sample and this is another random sample, and the result, the 72% and 52%, is also a random outcome. So we need to apply all those tools that we have established to properly answer the question whether this result gives us enough evidence that the green button produces more clicks in population than the blue one. Is this enough evidence? Or probably this is just a random deviation, and basically two designs are equal in their ability to produce these click rates. You see that even business tries to apply those experiments, and we really need to understand how we can compare two samples with the help of two samples, how we can compare the underlying parameters of these samples, whether the samples are different or whether they are the same, and whether the population parameters of them differ. Okay, so we start as usual with the simplest case when we have two independent samples and those are drawn from a normal distribution. So one sample of a size n, and we denote this with x's, is drawn from a normal distribution with the mean mu x and sigma squared variance. There must be parentheses. I have no idea why they disappeared. And a sample of size m that we denote with letters y, which is drawn from a normal distribution with sample mean mu y. And look, we assume that the variances are equal. So those two variances are equal. That's the first assumption. This is very important to understand. We will be watching into different cases. So first case when these sigmas are equal. Well, assume in practice that X received treatment and Y's are the control group. So like here. So X are those people who received the green button on their screen, and Y's are those people who received the blue button on their screen. Or X's are those who received some drug or vaccine, and Y's are the observations of those people who are in the placebo control group. Or back to our Friday example, X's are the salaries of people who received the master degree by the random assignment, and Y's are the salaries of people who stayed with the bachelor degree. Okay, so we assume something like this. So the effect of treatment is the difference between mu x and mu y, right? So that's the difference between mean value of this variable and mean value of this variable. What do we want to know? Whether this difference is not zero, right? So that's what we want to know. But first of all, if we have collected, those are population parameters. Those are unknown things. I hope you must keep this idea throughout the whole course. You must understand this. We don't know what is the true mu x, what is the true mu y. We want to estimate them. Well, we know how to estimate the population mean. We know that x bar, the sample mean, as the estimator for the population mean, mu x, and y bar is the estimator for mu y, right? So therefore, we can estimate this difference with the help of this estimator. So this is an estimator, which is a difference between sample averages, sample average x minus sample average y. Next, what do we want to know about the estimator? Who can say? If we have an estimator, this estimator is based on the random sample. The estimator is what in this case? Can anybody help me with the logic? What's coming next?
I mean, what?
Okay, so we have two numbers. Whether these two numbers are exact difference between the population means or not. Well, if you remember our logic, how we moved when we established the estimator, what was the next step? When we established the estimator, what is the next step? We know the estimator. What do we want to know about this estimator?
The deviation of the variance.
So first of all, we want to know the properties of this estimator, whether it's unbiased. What is the variance of this estimator? Because this is a random variable, and we really want to know. If possible, we want to know the distribution of this random variable. Guys, don't forget about this. Any estimator is a random variable. For any random variable, so the whole course of statistics was devoted for this. For any random variable, we must be able to establish the probability distribution and the corresponding properties of this probability distribution. So if you have this random variable, x bar minus y bar, we want the same. We want to establish the probability distribution of this. Well, first of all, yes, that's a question. What is the distribution of this estimator? Guys, please remember this idea. Whenever you see the distribution, the first question that must come to your mind is, what is the distribution of this estimator? Because this is a random variable and you must know something about this. Because only to calculate this is not enough. You must understand what are the possible deviations of these numbers from the center, and where is the center exactly, right? So where is the center is located. So what is the center of the distribution? This is an expected value of x bar minus y bar, right? So this is simple. The expected value of a difference of two random variables is what? Is the difference of expectations. We know that sample mean is an unbiased estimator of population mean, so therefore expectation of x bar is mu x, expectation of y bar is mu y, and therefore the estimator x bar minus y bar is unbiased estimator, right? So this is unbiased estimator for this population mean difference. Next, we want to know what is the variance of this estimator. Look, step by step, the variance of a difference of two random variables. So this is also covered in probability course. We had the review of this concept in lecture number 1. So if you don't remember, please refer to that. That's the sum of variance of y random variable and variance of the other random variable minus two covariances between these two random variables. So don't forget that there might be some dependency between these two variables. But, so let me jump a little bit. Because two samples are independent, and this independency is established by the random assignment of our treatment and control group, so you must behave in a way that your actions, when you create this experiment, your actions must ascertain that this covariance is gonna be 0. So there is no dependency between these two random variables. So therefore, if this thing is 0, we take this as a sum of variance x bar and variance y bar. And remember the first lecture, what is the variance of a sample mean? That's the population variance divided by the sample size. For variance of y bar, the same, population variance of the underlying random variable divided by m. So since we assumed here that sigmas are equal, we can take this sigma, factor this out, and in brackets we have 1 over n plus 1 over m, something like this. So that's a variance. That's a variance of this estimator under the assumption that two samples are normally distributed and independent. So as I said, in order to ensure that this independency, we need a randomized control experiment. We cannot just take some people, send them to study on the master level and some people not. We want to randomly assign them. In this case, we ascertain or we ensure that this covariance is 0, because otherwise we want to know what is this covariance, and well, it's going to be problematic. So therefore, we know that this difference is going to be normally distributed, is the mean which equals to this difference, and with the variance which equals to this expression. Nice. So we know the sampling distribution of this estimator under the assumption of normality. What is the problem here? The problem is that we don't know what is the variance. We have no idea about this variance. What should we do? Any ideas? If you don't know the population parameter, what should we do?
Estimate it.
Bravo, we should estimate this. Sigma squared is not known. We must estimate this from the data. And the estimator, so I don't have a derivation of this because it's kind of tedious and probably you don't really need this at the bachelor level at least. But trust me that this sigma squared is estimated with the help of something which is called the pooled sample variance. What is the pooled sample variance? Look, what is the construction? We have a sample variance of x. We have a sample variance of y. Then we multiply them by degrees of freedom, n minus 1 and m minus 1. And then we divide them by m plus n minus 2. Well, basically this is what? This is the weighted average of sample variances, because this is the weight of the first sample variance, this is the weight of the second sample variance, and then we have just the sum of these two weights, right? So n minus 1 plus m minus 1, which gives us m plus n minus 2. So weighted average of two sample variances. This is the estimator for this pooled variance. Okay, so now we know everything. We know what is the distribution of x bar minus y bar. We know how to deal with this sigma squared, which is unknown. Well, now we can establish all the necessary statistics for the construction of the confidence intervals and for making the hypothesis tests. So here is the definition. So we have, as we have discussed before, we have one sample of variables x of a size n, which is normally distributed with mean mu x and variance sigma squared. We have another sample, mu1 to mu m, with also which are independent and normally distributed random variables with mean mu y and variance sigma squared. So once again, I draw your attention that we assume equality of variances. Variances must be equal. And well, these two samples are independent of each other. yi is independent of the xi. So therefore, this is something that you are familiar with. This is a t-statistic, and this t-statistic looks like the estimator. Now it's x bar minus y bar, the estimator, minus the population parameter, and population parameter is mu x minus mu y. And this is divided by the standard error. This is not a standard deviation, be careful. This is a standard error of x bar minus y bar. So I will, and this follows a t distribution with m plus n minus 2 degrees of freedom. It's very similar to the t statistic for one sample test that we had on the previous lecture. But now you have just different estimator, this, and different population parameter, this. So what is x with the subscript x bar minus y bar? So as is here, so this is the square root. So basically, let me go back. So we know that the variance is this, right? So we want to take a square root of this variance, right? So that's going to be the standard error, but we don't know what is sigma squared. Therefore, we substitute this with the sample variance, that one that we have on the previous slide. And therefore, I just rewrite this thing here under the root sign, and we have this. So this expression, this square root of this expression, is exactly the standard error of this denominator, standard error of x bar minus y bar. So now, with the help of t-statistic, we can do whatever we want. We can build confidence intervals, we can make a hypothesis testing, and so everything is represented here. So under those assumptions that we had on the previous slide, and please take this, keep this in mind, that the assumptions are normality of two samples and similar or equal variances of these two samples. So under these assumptions, we have 101 minus alpha % confidence interval for this population parameter. So for the difference of this population means is the following. So that's our estimator plus minus t, which is familiar to you, must be, but now the number of degrees of freedom is here, and we multiply this by the standard error. Standard error from the previous slide, which is this long and seemingly difficult, but it's not. You see that that's just arithmetics to calculate this thing. So that's gonna be 100 times 1 minus alpha % confidence interval. Don't worry, I will show you the example how all these calculations must be done, and I hope that you will understand this good. So regarding the hypothesis testing, what exactly we want to test? Usually we want to test this hypothesis. Usually we want to test whether there is no effect in treatment coming from the treatment, right? So mu x equals mu y. What does this mean? It means that the treated group does not differ from the control group, from the placebo group. The effect is the same in population. That's our null hypothesis. So nothing has changed. Our treatment has no effect. Well, what is the alternative hypothesis? There are three different versions, as we had on the previous lecture. So either it might be upper tail alternative, one-sided, that the treated group has a larger effect than the control group. It might be lower tail alternative, that the treatment group has the lower value of the effect than the treatment group. Well, it's also reasonable, right? So probably here we want with the treatment group we want something positive to happen, right? So I don't know, the number of the click rate with the help of a new design of your internet page, or the salary that you receive with the help of master degree, for example. In this case, this type of alternative is reasonable. But for example, in this case, we want people to suffer less from COVID, right? So we give them a vaccine, and the length or the proportion of people who are ill, who got this COVID and have some negative outcomes must be less than for the control group, right? So be careful that depending on the question, depending on the practical situation, you either use this hypothesis or this hypothesis. Or if you are not sure which direction you are interested in, you just want to know that there is some difference, but well, you don't care what is this difference, either greater than or less than, then just use two-tailed alternative where mu x is not equal to mu y. That's all. Well, we know what is the test statistic from the previous slide. This is t. And the last thing that we want for the hypothesis testing is what? What else do we need as an element of a hypothesis testing? We have a null hypothesis, alternative hypothesis, test statistic. What else we need to make a decision? Does anybody remember last lecture?
Sorry, I don't remember.
Maybe somebody else. You're not alone, Vlad, here. Nobody. Vladimir, do you remember? What else do we need? No, probably you remember. Hey guys, just answer something. Yes, no. Don't be silent. Irina, do you remember? Guys, can you hear me? Vladimir,
Yes,
can
of
you hear
course,
me?
we can.
But why I don't hear from you anything? Just I don't remember, or I remember something. At least some response.
I don't remember.
Don't ignore me. Sinno, what
Sorry.
about you? Okay. Critical region. We need to know what exactly must be the region that this test statistic falls into in order to claim that our sample contradicts the null hypothesis, right? So we want to know for the upper tail alternative, the upper quantile of a t-distribution, and now be careful that we want this number of degrees of freedom. For the lower tail alternative, we want to have the lower tail critical region, and in this case, we want to know the lower alpha quantile of a t-distribution, or if we are interested in the two-tail alternative, then we take 1 minus alpha over 2 quantile, and we compare the absolute value of t with this quantile. Okay, so let's see. Let's get some example. Unfortunately I didn't have time to prepare your examples like the solved examples, but let's try to get some practical examples. So I took this I took this table. We are going to work with this table in econometrics, but well, I want to demonstrate you something. So suppose we have a random sample of how many people? Like, so 17,871 people. Quite large. So we have the data on their gender, age. Not sure what about MRD. What's that? Education, region, race, earnings, height, weight, occupation. So let's make the following. Let's test the following hypothesis. Well, we have earnings and we have gender. We can get two samples. One is the sample of males, another is a sample of females, and let's compare their earnings to understand whether gender somehow affects the difference in earnings, whether there is a difference between average salary for men or male and average salary for female. Quite decent question. Of course, well, if we want to do this properly, we will need to apply much more different things. We want to control for the region, for race, for something else, but that's going to be in econometrics. So let's do some very, very simple thing. Let's split this into two groups, males, females, and compare their averages. Well, we need to understand, just one second, we need to understand, where is that? Who is 0, who is 1, because, well, here we have gender 0. It's not quite clear who is 0. So yeah, 0 is female and 1 is male. Okay, nice. Yeah, MRD is marital status, married, widowed, divorced, and so on. Okay, nice. So let's go to Python. Let's do this analysis with the help of programming. It's going to be quite fast. So first of all, I need to load this table into as a data frame into the environment. So you are familiar with this part, what to do. I just give the address of this file as a file name. Then I use this function pd read Excel. And then if I want to see that everything is correct, I take this data head. That's, for example, 10 first entries. Well, we have this table here in front of us. So second thing that we want to do, we want to collect a sample of salary for males. That this variable sex must be equal to 1, and do the same for females. So let's call this sample X is males, and what exactly we need to do. So tomorrow on the econometrics, I will properly describe you how to do this filtering, and you will try yourself doing this. So now I need to do the following. I want to take, so you're familiar, for example, with the operation of taking a particular variable, right? So you know that if I want this variable earnings to kind of extract from the whole table, I just need to write this data and in the quotation marks earnings. And this chunk of code means that I'm extracting only these columns, earnings. But I want to do a little bit more. I want to take those earnings where on the variable sex I have 1, not all the earnings. I want to filter the necessary parts. What exactly I need to do? I'm kind of writing here between this data and the variable, I'm writing the condition. what kind of filter I want to use, and I'm writing the following. So data sex must be equal, and this logical equality is written with two equal signs, must be equal to 1. So what exactly does this mean? I'm taking my table data frame. I'm filtering out all lines where the variable sex is equal to 1. And then from the result of this filtering, I'm taking the variable earnings. So for those who are familiar to Excel, you can do the same here in Excel. You can just make it as a data table, and then you can apply this filter, tick 1, and you will see all the entries in this table where this variable equals to 1. Right, so it's also possible to do in Excel, but well, of course in Python it's a bit faster. So let's see what we have here. Let's take the 5 first entries. Well, exactly, right? So we have 1173rd observation. Well, it's 75th row here, but not counting for the first one. And remember that Python starts counting from 0, not from 1. And the number of earnings is exactly this, 28,560, right? So you can see that, well, exactly what we had here. And the same, we want to collect the sample of salary for women, for females. So the variable sex equals 0, so we call this y, and here I change this to 0. Okay, so we have extracted everything here. Nice. So now we have two samples. Well, I'm not discussing about normality of this sample, about the randomness of this sample, because this is the data. I don't know how this data was collected, but let's trust that this data was collected randomly. There is some explanation about the data here. Well, the data are taken from US National Health Interview Survey. Well, if there is a survey, so hopefully the survey has been done randomly, right? And the people who appeared in this sample, they are different. Well, it's not quite treatment, right? Whether the person is male or female, because you cannot control this. But let's assume that we are, so you can apply the same techniques basically for something that is unavoidable, let's say. At least nobody it's also random, right? So it's also random treatment whether the person is male or female. It's just, you know, given by God or by nature or somehow. So it's not decided by a person, him or herself. Therefore, we can, to some extent, take this as a random treatment. So now, what we need to do? We want to calculate the sample estimates, right? So we want to estimate X bar, we want to estimate Y bar, and we want to calculate this S, X bar minus Y bar. So let's go back slides to see how this works. So first of all, estimate the sample means. You know how to do this. X mean, right? Here is the sample mean for X, Y mean. Here is the sample mean for Y. Well, let's call them somehow average X, let's say, and average Y. Like these two, to give them names and print them, right? So average X and average Y. Okay, nice. So we have these two numbers. Well, we see that the average salary of males is slightly greater than for females. Now the question is this difference large enough to claim that males' earnings are higher than female earnings? Well, we don't know. We need to understand the sampling distribution of these two variables. So therefore, first of all, we need to calculate this thing. So let's calculate the standard deviation of x and y. So SDX is gonna be x S to d, right? As I'm not making a mistake. And SDY, well, we want variances, right? So variance x and variance y, sorry, not standard deviations. So variance x and variance y. So please remember that if you are using this on the pandas data frame, which is here, you don't need to specify the degrees of freedom. So by default, degrees of freedom are given, so this one is subtracted. But once you are using NumPy, you need to specify that the number of degrees of freedom must be 1 in this case. We had this several weeks ago on the tutorial, and I demonstrated you this thing. So please don't be confused. So here are the variances. One variance, the other variance. Well, they look quite close to each other, but as these two variances are also the sample estimates, we cannot be sure that these two variances are equal. So we will discuss this question a little bit later, how to understand whether variances are exactly equal or not. How we can we check this somehow? Can we check this assumption? At the moment we can't. And also we want to count how many observations do we have in males and females. So here we estimate the sample variances. And also we want to calculate the sample sizes. For sample sizes, we can do the following. We can call them M, N, and M. And we just use the function len. So len is for length. So how long is this? How long is this column? And len of y. So also bring n and bring m. Okay, so we have 7,896 males and 9,974 females. Good. So what is the next step? The next step is to calculate this pooled sample variance, this thing. Well, it's quite easier. Calculate the pooled sample variance. So let's see. Let's call this variance pooled variance. Let's call this like this. We have variance x multiplied by n minus 1 plus variance of y multiplied by m minus 1. That's our numerator here. And then we divide this by n plus n plus m minus 2. So let's print pooled variance. So here we are. So this is the pooled variance. Nice. What is the next step? The next step is to calculate the standard deviation standard error, sorry, of this estimator. So this is the pooled variance multiplied by this and then the square root. So compute, calculate the standard error of the difference, and that's in sample means. So let's call this SE. And the standard error, once again, is this. So it's a pooled variance. Pooled variance multiplied by this sum, 1 over n plus 1 over m. And then we need to take a square root of this, which is, so do I have math here? No. Well, we can use either math, as I taught you in the first tutorial, or we can use numpy sqrt, which is the same. So those two are equal. So let's print standard error. So we have the standard error for 105. Well, we have all the elements in order to build the confidence interval for this difference and in order to test the hypothesis. Yes, the last element that we need is this t y minus alpha over 2. So calculate the 1 minus alpha over 2 quantile of a t distribution. Well, let's assume that alpha equals 5%, just a standard choice for alpha. It's either 5%, 1%. And what we want and also degrees of freedom. Degrees of freedom is n plus m minus 2. So what's next? T, let's call this T critical, equals to, because that's going to be this critical value of T for the two-tailed critical region. That starts T ppf. I hope you're familiar to this function. We are using this many times. Y minus alpha over 2 and df. So print T crit 196, which is also the familiar number, because if the sample is large, usually you have 97.5% quantile around 196. What's next? Confidence interval. Well, 95% confidence interval for two-sided confidence interval. Confidence interval for the difference in mean salaries. What is the lower bound? Let's call this LB, lower bound. That's a difference in our averages. So average x minus average y here, then minus, or we can take this in brackets, so minus T critical multiplied by the standard error. We know that the standard error is here, it's SE. So the upper bound is exactly the same. I can copy this part, but with plus. Okay. Now let's print lower bound, upper bound. So here is the lower bound and the upper bound for the difference in mean salaries for between males and females. What we can conclude from this confidence interval? Who can say? Are males and females equal in terms of their average salary?
Yes.
How do you know?
Just an assumption.
No, you don't have an assumption now. You have all the results made by the statistic and built on the random sampling. So we have a result, we have a confidence interval. What are these two numbers? 2044 and 3632. What these numbers mean? What we have been calculating, come on, guys. I'm a bit surprised that you're probably losing the track of our discussions. What we have been doing?
We've been calculating the range, critical range.
Not range, come on, it's confidence interval. Be careful with the terminology. For what? What was the population parameter, unknown parameter for this confidence interval? Given our problem, what's that? Given our practice, you wanted practice, guys. Here is the practice. So, what was the question based on this data? Who can help to Vlad? Anybody?
So our
Vladimir,
question
are
was
you following us? Vladimir, are you following us? You usually also participate in our discussions.
to answer if the wage level is the same. So
For females and males, right?
yes,
Okay, so what can we say from this confidence interval? What is this? What these numbers precisely tell us? This 2044. This is what? 2044.
wage.
Whom wage?
I just
Whose wage is this?
both.
No. Look, the average wage of males is this. The average wage of females is this.
Oh, I see. But why
It's
did
like,
we call it lower and upper bound?
but because those are lower and upper bound for the confidence interval. We need to understand what is the object for which we have established this confidence interval. What this measures. I wrote it here, come on.
Calculations are
This is a
more
difference.
understandable
This is a
than
difference between mean salaries. Difference. How differ are mean salary of males and mean salary of females? So with this result, we can say that we are 95% confident that mean salary of males is larger than mean salary of females by how much? By
25%.
any number between
Oh.
these and this. We don't know the true difference, but we are 95% sure that this difference is bounded between these two numbers. So this difference is from $2,044 to $3,632. So that's what we have established. This is 95% confidence interval for the difference between salaries. So you have heard from the American media probably a lot of stories about gender inequality, about how women are how women are discriminated on the labor market. So there is an evidence here from this random sample. So there is an evidence that women are receiving, on average, a lower salary, and we have established 95% interval for this difference between the male salary and female salary. That's all. So now we are 95% confident that males in that in the United States are receiving more than females. I'm not sure whether we can extrapolate these results on other countries. We probably need to collect these samples for different countries. If you want to do the same research for Russia, you can calculate the random sample of salaries for males and females in Russia or China and do the same. And you will get some result, probably. Is this clear?
Yes. Only
So
the
guys,
beginning,
once
the
we are
variance.
going to practice, you need to understand the practice, not only calculations. You asked me all the last semester, come on, stop doing mathematics. We want to have practice. Here is the practice. So mathematics is just a tool, of course. You need to understand the whole world to know which questions to ask and how to answer those questions. Okay, so let's do one more thing with this sample. Let's
Sorry.
test it. Yeah.
Just I don't know, like maybe it would be more understandable if you somehow may show it graphically, where are we coming from and where are we going, where are we heading to, because it's just
What
really hard to understand.
what do you want to see?
I don't know. Let me describe it like that, or like graphically. Sorry, let me translate it.
Okay, let me probably show you one thing. Maybe that's what you want. Just a second. So I will. Yeah, it's box plot. X equals to sets. Y equals to earnings. Let's try if this would work. Yeah, data. I forgot about data. Data equals to data. Well, maybe this helps, but I'm not sure to what extent, if you wanted some graphical representation. So what do we see on this graph? So I wanted to discuss with you these graphical things a bit later, how to graphically represent what we can see in data. Well, if you prefer. So this is a box plot. So basically, each box shows us. So you see that on the vertical axis, we have earnings. We have the minimum earnings here. So this kind of line, so probably it's zero. I don't know. We have the median earnings, which are quite similar to each other, right? Here and here for females and for males. We have also the understanding how, well, let's say, how large is the deviation between salaries in females and males. You see that the salaries of males are less deviated, so they are kind of more compact. Let's say this box is just has lower height, and we also see this from the variances, right? When we calculated the variance of salary for males and females. No, wait, we had variance for females less also, right? So it's lower. Well, maybe, but at least we have this variation. The absolute variation is different. And well, and we see that the difference are, well, the average is quite close to each other. So these and these from graph. And we also calculated the averages here and here. They're quite close to each other. But does this mean exactly that these averages are similar? And with the help of establishing the confidence interval, we said no, even if we see that the salaries are close to each other, well, there is just $3,000 difference, basically not that much. But still, we know that in the population, the difference might be from 2044 to 3632 with the probability 95%. Well, there is still difference. Maybe economically it's not significant difference, right? I mean, economically $2,000 probably it's yearly salary, right? So it's annual salary. So maybe economically it's not that huge result, but still this is far from zero. And which means that these two samples, sample of males and sample of females, are different from each other. Maybe this would help.
By the way, but in this statistic, we don't study like the impacts in the job, etc., other properties.
No. At this moment, we are just talking about the difference between two samples. We are not discussing what are the reasons of this difference. No. And we even cannot say that the difference is because of the gender. That's the most important thing. Yes, please keep in mind that, and we will be discussing this here in statistics and in econometrics, that, well, maybe there are two different samples. Maybe, I don't know, maybe by chance. That's why in the data we have also the variables like the occupation, so where exactly this person works, race, region, because maybe this difference comes due to the difference not in genders but in the occupation of these people. So probably in males there are more I don't know, people from the finance industry, and females, maybe there are more people from some, I don't know, construction industry, and that's why they're having less salary. Or maybe those are older people, or, well, we are not discussing the reasons why these two samples are different. At the moment, we just established that there is a difference, and this difference is statistically significant, because the difference between population means is not zero. But we do not know why this difference comes and what is the source of this difference. No, we are not talking about this. Okay, so let me skip the part about the hypothesis testing because we are having 10 minutes to finish, and we have quite a lot of things to discuss. Well, as I said, we have assumed that two samples have the same variance. Well, we have calculated, based on this example, we have calculated variances. They are kind of close to each other, but we cannot say that they are equal, right? As here, the mean salary is very close to each other, but those are different. We have tested this. So what to do first? What to do if these variances are not equal? Well, if they are not equal, then we estimate the variance of this x bar minus y bar. So remember that was the equation here. We wanted to estimate the variance of this, and when variances have been equal, we calculated this variance as this thing, and we wanted to estimate sigma squared. Now, when we assume that these variances are not equal, well, we estimate it in a straightforward way. We estimate the sample variance of, we calculate the sample variance of x divided by n. This is the variance of x bar. And sample variance of y divided by m, that's going to be the sample variance of y bar. And well, if this estimate is used in the denominator of t statistic, so once again, this is somehow extended discussion of the statistics. I don't want to go deep into details of this, but trust me that the t statistic that we have calculated here, this one, does not have a t distribution, unfortunately, but it can be approximated with the t distribution. So it's not exact distribution right now, but it is approximate distribution. We need to calculate the number of degrees of freedom, and this is the way how we can calculate this number of degrees of freedom. It's not n plus m minus 2 anymore. It is this kind of not that difficult, but probably you need to look at this formula properly to understand how to calculate it. So we are using sample variances here, and of course we need to round this, because if this is gonna be not an integer number, we need to round this to the nearest integer. Well, but now the question is, how can we say from the sample whether variances are equal or not? That's the most important question, because these are technicalities. This is the mathematics. You can calculate this. You can watch the formula, plug everything into this formula and calculate. So Python will calculate you, or the calculator. The question is, how can we know that two variances are not equal? Well, here is a question comparing two population variances. Maybe, let me make a short pause. Maybe somebody remember that we have already discussed a statistic that is built on two variances. Vlad, do you remember? We have calculated t statistic, z and chi-squared. And there is also one statistic that is exactly made up from two variances. Which letter is that?
Z?
No, that statistic is a normal distribution. That statistic is very close, similar to t statistic. Okay, we have no time to discuss about this. So, first of all, once again, we assume two independent samples from normal populations. Our null hypothesis is that two variances, population variances, are equal. Our alternative hypothesis in this case is one-sided. Either one variance is greater or the other one is greater. For this test, we use F statistic. F statistic is the fraction of sample variances, X and Y, right? So let's do this straightforward in this example, when you still remember this. Test the hypothesis of about the equality of two variances. So we need to calculate this F, which is variance of X, variance X divided by the variance Y. Print F. Okay, so we have this number, almost 1. Now, we need to understand what is the critical region for this test. And for this test, we are taking the critical value of F distribution. But we need to understand what is the direction. Either we are taking the upper quantile or lower quantile. Well, if we see that s squared x is greater than s squared y, we probably, and if f value is greater than 1, we probably test the hypothesis that sigma x is larger than sigma y, because we know that s of x is larger than s of y. So how do we do this? We derive the f critical in the same way. So from the library stats, it's f, I guess just f, maybe not, let me check. And then ppf, well, we are taking 1 minus alpha, this right-tailed alternative, n minus 1, and m minus 1. Print critical. And now we have a decision. So it's 1, 0, 3, 5, 6. So this is our test statistic. This is the critical region. The critical region, anything that is larger than 1, 0, 3, 5, 6. What do we see? We see that our F statistic does not belong to the critical region. If our F statistic does not belong to the critical region, what we say, F is less than F critical. Therefore, we cannot reject H null, and we assume that two variances are equal, right? Because this assumption is not disproven, right? So we cannot reject this assumption.
Why don't you test the second boundary? The lower.
Well, because wait a second. So our null hypothesis is that variance, let's say sigma x, sigma squared x is equal to sigma squared y. So that's our null hypothesis. And the alternative hypothesis is right-sided hypothesis. So that sigma squared x is greater than sigma squared y. So because of this alternative, we choose only this critical region. We don't need to choose this. If you wanted to test as an alternative that sigma squared x is less than sigma squared y, then you need to take this critical region and you need to take the lower quantile. But in this case, it's not necessary. Why? Because s squared is greater than as s of x is greater than s of y, so we have f statistic which is greater than 1, because the left quantile is going to be automatically less than 1. So let me just demonstrate you that there is no reason to do this. If you calculate it, it is less than 1. So automatically our f statistic is going to be greater than this lower bound. It's just no need to test this. So that's how we can claim that our previous test was correct, because we have tested the equality of sigmas. We cannot reject this hypothesis that sigmas are equal. Therefore, all the previous calculation was correct. If we reject this null hypothesis, then we needed to calculate standard error in this way and degrees of freedom in this way. And you will do this on the exercise session as an exercise, what to do if the variances are not equal and how to deal with that. So now, the next question. Well, we had this exercise. How do we know that the distribution of earnings for males and females is normal? That's a question, because we build everything on the assumption that the distribution is normal. So guys, I'm asking you for 5 minutes just to finish our discussion, since we have started a little bit later, not to stop the lecture in the middle. So if you don't know whether the sample is normal or not, what we can do, we can use the central limit theorem. So everything that was on the previous slide is valid for small samples from the normal distribution. Even if you have like 5, 6, 7, 10 observations, but you know that this distribution is normal, then you are fine with these calculations. If you don't know whether the distribution is normal or not, as we don't know about the distribution of earnings, whether it's normal or not, what can we do? Well, if the distributions are not normal and the sample sizes are large, we can use t distribution or normal distribution because of the central limit theorem. That's why central limit theorem is important. Once you have a large enough sample, and we do, because this sample is large, right? So we have almost 8,000 observations in one sample and almost 10,000 observations in the other sample. It's quite okay. But look, this sample is large, but relatively small to the whole population of the United States, because in the United States, around 300 million people, right? And this sample is large, the number is large, but still it's relatively small to the whole population. So that's what we want. Well, for the large sample, everything that we have discussed before is approximately valid. Confidence intervals and hypothesis tests. So we are quite confident, let's say, that everything that we have established here is valid. All these calculations and our conclusion about the confidence interval and all these hypotheses. But if the sample size is small, distribution is not normal, we are in trouble. We cannot use all these things. Well, there are some techniques. We will probably discuss them a bit later. I mean, not today, but usually if the sample is not normal, or if you don't know whether the sample is normal or not, try to collect a large sample of observations. Because if the sample is small, all your conclusions are going to be just garbage. No any application. Now, what if we, instead of two samples, we have something which is called a paired sample? Just briefly, the logic is very similar to what we already have covered. So therefore, I will just briefly mention what to do. So what does this mean, a paired sample? So for example, if you have a medical experiment and we match people by age or weight or severity of conditions, and then one member of each pair randomly assigned to the treatment group and the other to the control group. So what does this mean? So that's what Vlad asked. How do we know what exactly leads to this difference in wages between males and females? We don't know because two samples are random. What we can do? We can make a pairs of males and females where all the other features of them are the same. We can take one female and one male who work at the same industry. They are of the same age, of the same education, of the same race, so all the features are the same, but one is male, one is female. And then we do these paired samples. So we kind of make two samples matching by all the features of the elements. Why? Because in this case, we can ensure that all these other variables do not affect the result. Or there is another possibility. In some applications, we want to see the effect before and after for the same object, right? So we want to, dynamically, we want to collect the data on some sample of people, let's say, before a treatment and then after the treatment. In both cases, we have something which is called a paired sample. So for this paired sample, first of all, these samples are going to be dependent. So we fail the assumption which we made on the previous slides about the independency of samples, right? So the previous analysis does not apply. On the other hand, it's much simpler, and this analysis has much better, let's say, applications. Look, the pair design is the following. So we make the pairs X and Y i's. So those are now not two random samples. This is one sample of pairs Xi and one Yi. We assume that x's and y's have these means mu x, mu y, and variances sigma squared x and sigma squared y. we assume that different pairs are independently distributed. So the pairs are matched by their features, but one pair is independent of the other pair. And then there is some covariance between xi and yi, which means that these samples are dependent. And we denote the differences as di. So the differences between two observations is di, and this difference must be independent. It gives us very nice thing. We denote expected value of di as mu d, and expected value of and variance of di as sigma squared d. So this is a notation, right? We don't know mu d, we don't know sigma squared d. That's what we want to basically infer about. And then look, under the assumptions from the previous slide that we have stated, there is a confidence interval for this d bar, for mu d, sorry. We need to calculate the sample average of d. Very simple, very easy. You just have n differences, you calculate the sample average of them, and then you do the familiar thing. So this is similar to the confidence interval for the population mean. But instead of x, you have difference. You have another variable, d. That's just, we know how to deal with that. Regarding the hypothesis testing, we want to know whether this difference in population is zero, right? That's a reasonable question, because in this case, there is no effect of the treatment. And well, we want to test one of these alternatives, whether the effect is positive, negative, or just non-zero. Test statistic is simple. It's just d bar, the average, minus 0 divided by this standard deviation of d over square root of n. Exactly the same as usual t statistic for the population mean.
Is it
and the
minus
critical
0?
regions. Yes, minus 0, because, well, I could have written
Okay.
here d bar without 0, but you remember that we take the estimator minus the population parameter. So we assume that the population parameter is 0.
Yeah, okay.
In this case. The critical regions are the same as usual. Nothing is different here, so I can just jump to the other slide. The last thing, the very last thing for this topic, briefly. We also sometimes want to compare two binomial parameters for two samples if we have some proportions. We started with this, the click rate for one side and for the other side design. The click rate is the proportion, right? This is not the population mean, or it is a special version of a population mean. Well, in this case, we apply the same techniques. The only one difference is in the test statistic. Well, we assume that we have two samples. Those samples are drawn from the binomial distribution with n and p of x and with m p of y. And we establish the 100 1 minus alpha % confidence interval for this population difference in the population proportions as the following thing. It's the difference in the sample estimates of these proportions plus minus quantile 1 minus alpha over 2 quantile of the standard normal distribution multiplied by this. What is this? This is the variance of x over n plus variance of y over n. Exactly the same as we had here. So let me jump a little bit back here. That's exactly the same as here. And if you want to test the hypothesis about two binomial proportions, we do the following. First of all, usually the null hypothesis is that two proportions are equal. Alternative hypothesis is one of these, depending on what you want to prove, whether one proportion is greater or the other, or they are just not equal. Well, we use that statistic, which is built. If you can see the parallel, it's very simple to similar to that statistic for one sample proportion. It's p hat x minus p hat y. This is the estimator of this difference minus the difference in population. And if under the null hypothesis we assume that they are equal, so this thing becomes 0. That's easy. And here we calculate the variance of sample variance of one and the other sample, and then critical or rejection region. Well, I took a little bit longer, but we have covered the whole thing about the testing two samples. So tomorrow on the econometrics, we will do something similar based on the other data set, not about the earnings and not about males and females, but on the data set that we are going to use throughout the course of econometrics in the next lectures. So, and you will do the exercises on the exercise session regarding these hypothesis tests and regarding the comparing of two samples. Don't forget about your bonus extra quiz tomorrow. Watch lecture number 7. Try to digest those ideas about the hypothesis testing. I see that there is some confusion here. And yes, that's all. See you tomorrow on the exercise session for econometrics.
I have questions.
Go on.
So,